Morning, Physics 20. Welcome back. Well, technically it's afternoon, but that's irrelevant. You guys are watching the video. It could be any time of day. All right, so ladies and gentlemen, welcome to the third set of notes in Physics 20. We're going to be looking at graphing uniform motion. This is why we spent so much time on the review with graphing, because we're now going to be applying that lovely knowledge to this stuff. So, ladies and gentlemen, please enjoy the meme. It had to happen. I love these things. So always label your axes. Get it? Light axe, heavy axe, double axe. Okay. Good for D&D players. I know. D&D is awesome. So is Pathfinder. Same thing, different brand. All right. So ladies and gentlemen, when we're going to be looking at uniform motion graphs, remember we're still going to be dealing with our equation V equals D over T. But now we're going to be looking at this data on graphs. Okay, so graphs, these things can contain all sorts of information about the kind of motion that an object is going to be undergoing. All right, so when you're going to be doing calculations with graphing questions, you need to consider the following three things about that graph. Okay, you're going to need to consider the axes of the graph. What are these axes telling you? Okay, so you're going to have to read those carefully. You might have to calculate the slope. It depends on what you're looking at. Remember, you need 2 points to calculate a slope. And also recall that your slope is your rise over run, or your change in y over your change in x, or your y2, whoopsie, there we go, y2 minus y1 over x2 minus x1. All right, this is on your data sheet, so you do not need to memorize this. Okay. Another thing you could calculate as well is going to be the area under the graph. So essentially what this is, it's...
Megan Connect, please call 102.
Sorry, announcements. So the area under the graph. So what that means is essentially between the line and the x-axis. So if I have a graph that looks like this and then goes like that, that is the wonkiest graph I've drawn all day. That even looks really bad. Let's fix this. Okay, that was ridiculous. Let's try that again. There we go. I have a blue line. There's my axes. There's my y. There's my x. And I have a graph that goes like that and then like that. Okay. So,
Victoria, can you please call 102?
More announcements. And we're looking at the area under the graph. What that really means is between the line and the x-axis. So it means that this pink region here, that x-axis there,
Karen Gorman, if you can come to the library when you get a chance, I have your books for you.
Lots of announcements. Okay. So then this line here would also be under the graph too. So remember that it's between the line and the x-axis. That is super important. All right. Okay. So, ladies and gentlemen, if you need to calculate the area for something, you might need to break a shape down into multiple different parts, okay? So you may have to use your area of triangles and squares or rectangles in order to get the proper area, all right? Okay, so ladies and gentlemen, why are we talking about slope and area? Because, ladies and gentlemen, on a graph, if you need to calculate anything directly off a graph, you must use slope or area. Do not use equations on a graph. This is very important. We're going to write this down. So don't use equations, okay, on graphing questions. So if you use V equals D over T On a graphing question, when you need to be using slope or area, you get 0 points. I'm serious. I'm truly serious. Because that's the wrong strategy. If you happen to get the right answer, it's serendipitous. Okay? You have to use slope or area at the right times. You can't use equation when calculating directly off a graph, okay? So be aware of that, all right? Okay. So, ladies and gentlemen, there are 2 types of graphs that you are going to see with your uniform motion, okay? So when you're going to be representing uniform motion with graphs, you will see a distance versus time graph or a velocity versus time graph, okay? So there's your 0, and this here is going to be your distance. And you will also see this as a displacement. So you can see this as distance or displacement. The graphs are going to look the same. All right? Okay. So we can have motion that could look like this. Okay? Like that. And then like that. Okay. So let's analyze this graph here. And let's look at some of the key points. So, what do we have here? This is going to be a slower speed because of the shallow slope, okay? The slope, ladies and gentlemen, remember that your slope, okay, is your rise over run. So the steeper the slope, the higher the speed. Cool, hey? So we have 2 slopes that we could look at. We've got this one. Oops, I'm going to stick to using blue there. There. This slope is steeper than that one. Okay, we can even make that look a little bit steeper. Let's make it look steeper so it's more obvious. There we go. Okay, so this is a steeper slope. That is a faster speed. However, what do you notice about it? It's going backwards. It's going in a different direction than we were going here. Okay, because here we're going in a positive direction, so we could say that's east, and here we're going in a negative direction, so you're then moving west. Cool, hey? And 0 is where you start. So remember that your slope is equal to y2 minus y1 over x2 minus x1. Well, if this is in meters and this is in seconds, your time, well, ladies and gentlemen, what is this? But this is a change in the y. Well, the y is a change in distance. What is the x? But on the bottom, it's a change in time. Look at this, d over t. Your slope is going to equal your speed or velocity, depending on what the question's asking and how you approach that question. Okay, so ladies and gentlemen, your slope is going to equal your speed or velocity on a distance time graph or a displacement time graph, okay? So that's super important, okay? So if I give you a graph like this, and I will, and I say calculate the speed at this time, what I want is the slope, all right? Okay. So let's look at some other key points on this shape of graph. An object is going to be at rest when the graph is horizontal. So when we look at this graph up here, notice here, that's the horizontal spot. That's when the object is at rest. Because if that is 5 meters, you're 5 meters away from where you started. You're still 5 meters, still 5 meters, still 5 meters, still 5 meters. Your distance hasn't changed. If you calculate the slope, you're going to get 0 on a flat line. So that means, ladies and gentlemen, you have 0 speed, okay? So if you're flatlining here, you're still at rest. You just haven't gone anywhere. You're flatlining here. You're still at rest. You just have farther away from where you initially started.
Office 102. Mr. George, call the office 102, please.
All the announcements. All right. Okay. So let's also look at this last piece here. So an object is going to change direction when the graph changes direction. All right. Well, let's look and see our graph here. Where is our direction change? You guys find it? Good. Right there. That point.
Just a reminder, if you want a hard copy teacher plan book for next September, it is the last 10 minutes to let me know. Thanks.
All right. So, ladies and gentlemen, that is the change in direction. Okay, so here we're going west, or east, excuse me. Going east, going east, going east, going east. Standing still, standing still, standing still. Now look, we're now going west. There's west. We're going towards the west now. So that is where your change in direction is. All right? Okay. Ladies and gentlemen, I'm going to give you guys another lessons at Lent. On test. On your first quiz, in written response, I'm going to give you guys 2 graphs. And on those graphs, I'm going to ask you a series of questions about them. Those are the things you are going to need to know about that graph. One of those graphs. Cool? Cool. Another way, ladies and gentlemen, that we can look at uniform motion in a graph is we can look at a velocity versus time graph. So where here, that's your velocity. Now this could also be speed versus time. It just depends on the scenario, but your pattern on the graph would be the same. And this would be time. All right. So in this case, for uniform motion, we're only going to be looking at uniform motion here. You could have, we'll be looking at accelerated motion later. So you could have a line going that way. And then a line going this way. Okay. Oops. I wanted to change this up a bit. I wanted to have a period on the x-axis there. There we go. Okay. So that is more what your graph is going to look like for uniform motion as velocity versus time graph or a speed versus time graph. Now that's 0. Okay, here we could say this is east in an easterly direction, and this is going to be west. Now on a velocity versus time graph, you can use area. Okay, we're not going to use slope on this graph yet. That's going to be later. But for now, we're going to look at area. Well, remember that area, length times width, equals the area of a rectangle. Okay, well, let's look at our axes. Velocity times time. And if I was to calculate the area of this, I'd be measuring from here to here, and then multiplying that from here to the distance from there to there. Length times width, right? Well, what's that? Velocity times time. So velocity times time is equal to what? Displacement. So ladies and gentlemen, your area is going to equal either distance or displacement, depending what the question's asking for. Neat, eh? Yeah. Okay. So when you're going to be doing area, you can either use your area of a rectangle, which is length times width, or you can use your area of a triangle. We're not going to use triangles right now. We'll be looking at those in a few videos from now, a few lessons from now. But remember, the area of your triangle is length, or it's like, base times height divided by 2. Okay? Okay. You don't even have to memorize your equation for area. It's right there on your data sheet. Sounds good? All right. So, to find the total area, ladies and gentlemen, you would have, I want to change colors there. This would be your area 1, this whole area that I'm etching off in blue, okay? And then, well, we would have to kind of draw an imaginary line here to finish out our graph. And then this would be area 2. Now, notice here we have negative values. So when you're going to be finding the total area here, you'd have to find the area of here plus the area of here, keeping into mind that that y is negative. All right? Okay. So, ladies and gentlemen, a couple of other key points. What you're going to need is when an object is at rest on a velocity time graph, when it's on the x-axis. So that's very different. Now, this is where I tend to see most of the confusion here, is that the difference between reading the two graphs, okay? The two are very different, all right? Now, velocity, this is the velocity time graph. If your velocity is 0, are you moving? No, you're not. On a velocity time graph, the only time you are at rest is when you're on the x-axis. Up here, well, if this is 5, well, 5 meters per second, 5 meters per second, 5 meters per second, you're moving uniformly, but you're still moving. Your velocity is 5 meters per second, okay? So this is pretty tricky stuff. There's a lot going on here. All right, so the object changes direction on a velocity time graph when you cross the x-axis, okay? That's super important, when you cross the x-axis. So when we come up here, where do we go across the x-axis? Right here. That is where we cross the x-axis. That is your change in direction. All right. Okay. So, ladies and gentlemen, we're going to write another piece here on test. You 100% guaranteed need to know this stuff. You are going to see graphing questions on your assignment, your first assignment. You are going to see graphing questions on your first quiz. You're going to see graphing questions on your unit test. You can't escape them. In Physics 30, we're going to be doing graphing questions, and they're going to be harder. This is important. And we're not even done graphing yet. We still have to get into our acceleration graphs too. So take your time with this. Study this, study this, study this, study this. Do practice problems, okay? And see me if you have questions. All right? Okay. All right, so we're going to answer a few graph questions here, ladies and gentlemen. Now, I'm going to need you guys to have your notes out and available, okay? So then that way I can draw on this while you're following along with the questions you're going to be looking at. So I'm assuming you guys already have your notes out and you're already taking notes, pausing the video where you need to fill in your notes, okay? All right. So, use the following graph of the motion of a sailboat to answer the next questions. The sailboat is initially heading east. Okay. So, we have kilometers and we have hours. We're going to leave time and distance in the units they are. They're in appropriate corresponding units, kilometers and hours. Okay. So, when you look at your notes, you'll see question A, where which section of the graph shows the sailboat having the greatest speed? Now, remember, ladies and gentlemen, what does greatest speed mean? How would we know? Steepest slope. So look at this graph. Where is the steepest slope? From C to D. Oh, let's label them actually. I have them labeled on my notes here. So we'll give this point A, B, C, D, E. So this guy here is your greatest speed. Okay, so in your notes, what I want you to do, you come down in here and you see where is the greatest speed. That would be C to D because it is going to have the greatest slope. All right. All right. Now, what times does the boat change direction? So, no time bracket S. So you can have one or more points. Okay. Let's look at our graph. When on a graph, now notice, ladies and gentlemen, this is a distance time graph. So that means, go back in your notes, have a look. What did we write previously? When do we change directions? On a distance time graph. When the line changes direction. So in this case, our line changes direction at point C. Okay? All right, so well, at point C, scroll down, that's 1.5 hours. As the question says, at what time? So that means I want at 1.5 hours. That's when the boat changes direction. All right? All right. Okay, what time or time? So that means I want all times the boat is at rest. Okay. Well, remember, ladies and gentlemen, that when on a distance time graph, when the graph flattens out is when an object is at rest. So that is at rest. So that is from B to C. So that is from 1 to 2. Oh, not 1 to 2. 1 to 1.5 hours. Okay. As the question says, from what times? All right. So 1 to 1.5 hours. So where that graph is flatlining. All right. Okay. And calculate the sailboat's velocity at 2.5 hours. Recount your answer to 2 sig digs. All right. So I'm just going to answer this question up here beside the graph because that's going to be easiest. Now I've asked you to calculate velocity at 2.5 hours. Okay? Okay. Let's find 2.5 hours on the graph. Right there. What do I do? If you said calculate the slope, 5 points for Gryffindor. If you said use v equals d over t, I'm sorry, but I'm crying inside. I'm sad. Okay? Slope, 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 slope. Never, ever, ever use equations when calculating directly off a graph. Okay? So I need the slope of that line. Okay? I am going to pick 2 points that are far away from each other. I'm going to pick the farthest 2 points because it's the easiest. This point here is right on that line. It's intersecting of 2 grid lines. That's easy. I'm going to pick this point. It's intersecting of 2 grid lines. Easy. Now the question says velocity, so that means I need direction. This is also important. When you have a negative line like this, you need to make sure your values are put in the correct order. This is point 2. This is point 1. All right? So your 2, your second point on the graph is farthest along the x-axis. Okay? So when I'm going to write my slope equation, which is my y2 minus y1 over x2 minus x1, well, my point number 2 that I have selected, so we'll say P2, is on my y is 0, and my x is 3. Okay? My point 1, which is this one, okay, my y is 5, and my x is 2. Okay, so those are the 2 points I've selected. Now, when I go and calculate my slope, I need y2, so that would be this one, so 0 minus 5. I then divide by my x2, which is 3 minus 1. Okay? So our slope is going to be negative 5 over 2. And, ladies and gentlemen, which is going to give you... Okay? It's going to give you... Come on, calculator. I don't feel like doing the math right now. I wrote this down wrong. Sorry, I'm having a brain fart. I wrote 1. That should be 2. I hope you guys caught that. Okay. Okay, so that should not be over 2. It should be over 1. I was wondering why my numbers were seeming really weird. Okay. So then that is going to give us a slope of -5 kilometers per hour. Okay, kilometers divided by hours. All right. So I need to write this appropriately with direction. So my speed is going to equal, now I need to, the question asked you for 2 sig digs, so 5.0 kilometers per hour. And it's negative, and the object is initially moving east, so that means it's going to be west. Alrighty. Okay. So we're now going to go look at our next graph here. Oh, excuse me. I missed a piece. Excuse me. It's Monday. All right. So this next piece we're going to look at is calculate the distance traveled at 2 hours. Okay, so I'm going to jump back up here to our graph. And it says the distance traveled at 2 hours. Well, how would we do that? Well, let's have a look. Here's 2 hours. I'm going to switch colors again. I'm going to use pink. I haven't used pink yet. There's 2 hours. This is the distance time graph. This one, I want to calculate distance. Well, if I can't really calculate area here, it'd be distance times time. And distance times time is like meters time, meter as a meter second, and that's not helpful. We want velocity is meters per second, not a meter second. So, well, but what we can do is we can read our graph. Well, look here. From here to here on the graph, ladies and gentlemen, we traveled from 5 kilometers to 10 kilometers, so that's 5 kilometers. Here, we traveled 0 kilometers. Now, remember the question said distance, so we don't want direction. And then we went from 10 kilometers back to 5. So what's the total distance? 10 kilometers. So the distance here is 5 plus 0 plus 5 kilometers, which is going to give you a total distance of 10 kilometers. Okay? Okay. That's the distance. All right. Now, notice we weren't calculating anything directly off the graph. We had to read the graph. That's graph reading, not graph calculating. The question also asked you to calculate the displacement. Well, this one here, we went 5 meters going east, and then we went backwards 5 meters after going 0. So we have positive 5 meters plus 0 meters from when we're at rest, plus our negative 5 meters, okay, from going backwards. Well, 5 plus 0 minus 5, that is going to give you a displacement of 0 kilometers, or kilometers. It should all be kilometers, not meters. Okay? 0 kilometers. And it's okay to have a displacement of 0 kilometers. That's fine. Because this guy wound up right back where he started. It's as if he went on a sailing boat little loop, went this way and then went that way. All right? Okay. So, let's go down and look at our last question here. Calculate the average velocity between 0 and 3 hours. Round your answer to 2 sig digs. All right. Well, here we've looked at average velocity. Remember, ladies and gentlemen, that average velocity is equal to displacement total, okay, divided by time total. Well, ladies and gentlemen, we've only done part of it. We've only done distance and displacement at 2 hours. Okay, let us calculate our total displacement over the 3 hours. So I'm going to go back up to the graph here. I don't have any space left to do calculations directly up here, but we have enough space to do some reading. We've already done part of it. We've done up to here. So plus 5, 0, minus 5. Okay, let's put that in there. Okay, so we've done plus 5 meters, kilometers. I'm getting my units wrong. I'd be deducting myself half a point here. Plus 0 kilometers. Okay, and then we're gonna jump back up for the negative 5. And then let's look at this last stretch. We've gone from 5 here and then all the way down to 0. So that's another negative 5. Okay. So plus negative 5 plus negative 5. Okay. Well, 5 plus 0, 5, minus 5, 0, minus 5, negative 5. So the displacement here is negative 5 kilometers. So our displacement total is negative 5 kilometers. We can put that in there. And the total time, 3 hours. And that is going to give you, ladies and gentlemen, negative 5 divided by 3. It's going to give you 1.6 repeating. Well, we need to put this in 2 sig digs as 1.666666666, right? So, and you also got yourself a negative number. All right. So, we need to round this. We want 2 sig digs, so that 6 is going to round that up. That's 2 sig digs. Your units are kilometers per hour. And we have a negative, and the object is initially moving east. So that is going to give you a direction of west. Sounds good, guys? Alrighty-o. So what I would do now, ladies and gentlemen, is we've already done a lot of work here. What I would do, I'm going to pause the video for a bit. Go and practice some of these questions here. Okay, these will be some distance time questions, and then you can get some good practice with distance time graphs, and then we can go back to the lesson to look at your velocity time graphs. All right? Okay, so ladies and gentlemen, pause the video and come back. We're back! Awesome! I'm assuming you've paused the video and you have gone and done these practice questions. Okay. So let's go and look at our next graph here, ladies and gentlemen. So this is a really tough one here, as we're now going to be looking at a velocity time graph. All right. So with this velocity time graph, we can definitely do things a little differently than with a distance time graph. Okay. So we have velocity here, and we've got time here. Okay, meters per second. Okay, so question A, at what times does an object change directions? Now, this is a tough one, ladies and gentlemen. Remember that when an object changes directions on a velocity time graph, it has to cross the x-axis. So here we go. We've got a time there. That's crossing the x-axis, and there is crossing the x-axis. All right. So the 2 times that we've got there that's about 240 seconds. And that one's about 360. Okay. All right. The only time we've crossed that x-axis. What times is the object at rest? Well, when is an object at rest on a velocity time graph? When its velocity is 0. Okay, so, well, here our velocity is 5. Oh, there we go. And that's about 90 and about 150. It's about 90 seconds to 150 seconds. Now, do we have any other times where our object is at rest? Yes, we do. From 300 to our 360, we're running on the 0 axis there, on that x-axis. All right, so that is our 300 seconds to 360 seconds. Okay? All right. Okay, now what is the velocity at 180 seconds? Well, this is going to be different because, ladies and gentlemen, this is a velocity time graph. This is a velocity time graph. We don't need to calculate anything to get the velocity, we just read the graph. So the question wants 180 seconds, so I find 180 seconds and I go up here, read over, it's about 6.8 meters per second. Okay, so for that one, it's a velocity time graph. So all I had to do is read the graph. Now, I made a mistake here. What would I be deducting half a point off myself for? Direction. I did not write down the direction. I asked for velocity in this question, which means I need direction, because it is a vector quantity. So when we scooch up here, this object is initially traveling south. Well, here, that would mean that's south, and then down there is north, so that would mean if you're up on this part, you're going south. So that's what I mentioned, how we don't say always when it comes to our graphs, or our directions. I guess sometimes, because you can definitely make south positive. Okay? All right. So our next question, ladies and gentlemen, these next two are tough ones. Okay, I just got to pause filming here. I'm getting pretty thirsty. My throat's getting sore from all the talking. I'll be right back. All right, we're back. Last question. Or last two questions, actually. So we've got, oh, come on, computer. There we go. Record the total displacement from the object from 0 to 300 seconds. Okay, so this, ladies and gentlemen, is going to be a bit of a tough one. All right, there's going to be a lot of math here, so let's scroll on up. All right, so I said displacement on a velocity time graph. Okay, so ladies and gentlemen, when we're going to be dealing with displacement, velocity times time gives us displacement. So that means we are going to need area. Okay, I'm going to do the calculations for this one up here beside the graph because it is going to be a little bit easier. All right, a bit more space so that way we can read right off the graph and write things down as we go. All right, so we're going up to 300 seconds here. So that means we are going to have 3 areas that we are going to need to be paying attention here. All right, well, our displacement is going to equal our area total, which is going to be the sum of area 1, area 2, and area 3. Okay, so area 1, ladies and gentlemen, well, area of 1 is our length times our width. So 0 there, okay, to over here, well, that's 90. Okay, so that is 90 there, and here is going to be 5. Okay, so area 1, length times width. Okay, so length times width of object 1 plus length times width of object 2, that's 1, plus length times width of object 3. Okay, so our area total here, we have 90 times 5 Okay. Now we're going to come over here. We're going to look at area 2. Ladies and gentlemen, this is not going to be straight up 240. Okay. We have to do some math. We've got 240 here, but what are we here? 150. So in order to find this distance here, we need to go our 240 minus 150. So watch very closely for that one. Okay, so what that is going to give you is another 90 seconds from here to here. Okay, so this would be 90 times 6.8. Okay. And then we have a third area to contend with. Now notice here we're going into the negatives. Okay, so this guy we've got 300 to 240. So you're going to need to find the difference there, which is going to be 60 seconds. Okay, all right. So that would be your 60 seconds times, now this is going to 3.2, but that's negative. That is negative 3.2. So plus negative 3.2. Because the question says displacement, not distance. So that means we have to take direction into account, and that's going down past 0 into the negatives. So you're going to put all that into your calculator, and you are going to get your 90 times 5, which is going to be 450 meters. Plus your 90 times 6.8, which is going to give you your 612 meters, plus your 60 times negative 3.2, which is going to give you your negative 192 meters. Once you add all those three together, you are going to get 870. Now we want sig digs, okay? Let's see, what did I say in the question for sig digs? I said 2 sig digs. All right, now because I want 2 sig digs, that's 3. So I want 8.7 times 10 to the power of 2 meters. And I wanted displacement, so that means I want direction. And the object is initially traveling south, so that means south is positive. All right. I know this stuff is tough, ladies and gentlemen. There's a lot going on with this. All right. It's pretty tough. Okay. All right. So one question left. What is your average speed of the object from 0 to 300 seconds? Well, we have an advantage here. We've already done half the work. Average speed is distance total over time total. Well, we've already went and calculated our displacements previously. We already did that. Except, ladies and gentlemen, we're not going to have to scratch a negative here. Okay, so these values we are going to get from part D. Okay, so we're already going to use those. Use them again. So we first had 450 meters, and then we traveled 612 meters. But remember that 912, or the 192, excuse me? That was negative. But I said speed. So that means I want scalar, which means no direction, so that's all positive. We're going to divide that by the time total, which is 300 seconds. So our average speed, ladies and gentlemen, my back is killing me. I've been sitting in the same chair all day filming videos. Okay. So our VF is going to be, once you plonk all that in your calculator, is 4.18 meters per second, but I want 2 sig digs. So that is going to round that up, and we're going to get 4.2 meters per second. Sounds good? Okay. Ladies and gentlemen, that is the last of this video. So I hope that you guys found that interesting. Hope you guys enjoyed it. So there are some practice problems for you guys to work on out of your workbooks. So give those a shot. See how you do. Check your answers in the workbooks. If you guys have any questions, make sure you come and see me. This is not the last that we're going to be seeing graphs. And these questions that you see in your notes are pretty much the exact same style of what's on your assignment and what's on your quiz. The graphs will be different, but some of these questions are going to be pretty much identical. So lessons on hand, this is on your test. Make sure you study it, please. Okay, ladies and gentlemen, I hope you guys have a good rest of your day and no fires, injuries, or explosions. Talk to you later. Bye.